So, okay, in this video we will cover the Thiessen method of aerial precipitation analysis. So, I hope you know what is the aerial precipitation analysis. Just to give you an idea, in aerial precipitation analysis, let's say this is the catchment area or the boundary of the city, and you have located certain rain gauges at certain points. Let's say this is the rain gauge A, this is rain gauge B, and this is a rain gauge C. Now you are recording rain, or precipitation in general at certain points at certain location. This is one of the location, this is the second location, and this is the third location. Now you want to estimate the average precipitation for this whole region, for this whole catchment region, for this whole city, and for this whole area. So how you basically go about that? So if someone asks you what is the aerial precipitation, what is the average precipitation in this region, in this city, you're not gonna directly tell them that okay, so this rain gauge has collected a rainfall of, let's say, 48 inches in this month, or this year average precipitation in this year. So the city has a precipitation of 48 inches. No, it's not gonna be that simple. Or you're gonna just call out the recordings of this rain gauge or this rain gauge. So what we do in real life, we basically average the precipitation data from all these three stations, so we have an idea of the average precipitation that has taken place in this whole region. So for doing that, you have basically three methods. The one of the method is the very simple. The simplest method is the arithmetic mean method. In arithmetic mean method, what you do basically, you sum up all these rain gauge data and you divide them by the number of stations. This is the simple average that we have been doing in our elementary maths, in our schools, and in most of the cases in hydrology also, when the relative distance between these stations is close and they are not located very far away, and if the region is if this area is relatively a plain region and the variation in precipitation is relatively low, and there is not a abrupt change, there is not a very huge change between the precipitation data between any two rain gauge station. So in that case you can go with arithmetic mean method. But if you want to get an idea, a more closer idea, a more accurate idea of the aerial precipitation, you go for Thiessen polygon method or isohedral method. In this particular video, we are only going to cover the Thiessen polygon method. So in Thiessen polygon, what you do basically, you divide this whole area into sub areas. Let's say this is one of the areas, and this is the second area, and this is the third area. So we assume that this region, this small area, is influenced only by this station, and this area is by this one, and this area is influenced by this region. So we go for some statistics, we apply formulas, and we at the end of the day come up with the aerial precipitation, the average value for the precipitation in this whole region. So this is the idea of Thiessen polygon. So in QGIS today, we would have been having a catchment area like this one. Then we would locate points, the rain gauge points. Then we are going to be drawing Thiessen polygons like these. These are the Thiessen polygons. So these are the Thiessen polygons. This area is influenced by this station, this one by this one by this, and so on. See, this is my catchment area. Okay, this is the boundary of the city, this is the catchment area, and we have located these points. For example, these are my points. I will show you how to add these points first. I hope you know how to add the point layer, but just to help you out, I will go to this new shapefile layer. Okay, click on this, then you will be having an option to name this file. Let's say this is a point data. I am in point data 2 for me, because I have already a point data layer present in my QGIS, so I am naming this point data 2. You can name it anything you want. This is my point data 2. Okay, and then this is UTF-8, so don't change this value. And then in the geometry type, we have this as a point geometry, because we are locating points, we will be drawing points basically. and APSG 4326, just to avoid a confusion and just to avoid miscalculation, change this to project CRS, that is 3857. You can see bottom of my screen, the right bottom of my screen, I have my project as 3857. So I am keeping the layer same, so to have uniformity in the project. Okay, so this is created. We have to add two columns to the attribute table. One column would be like location, where these are located. That would be a text data, because location is to be put like the point location, the city location. And the next thing, we have PPT value, precipitation depth of PPT. Let's say it is precipitation depth. Okay, and this is gonna be a decimal number. Add to field. Let's say we want to delete this ID, that is integer 10. We don't need this. Okay, remove this field and say okay to this. Okay, now this layer has been created. Now what we have to do is to add points of rain gauges here. Okay, so click on this pencil icon, and then you would have an option of creating add points feature. Okay, and then let's say we want to add one point here. We will be directly given a dialog to fill up the location data for this. Let's say this is location A. Let's say okay, and it has precipitation depth of 50 inches, for example. So this is one point is added here. The next point we wanna add is here, and this location is B location, and it has precipitation depth of, let's say, 45 inches. Location, let's say we have located this location here, and this is location C, and it has precipitation of 40 inches. Of course, if you want to realize the real-time data, you would be having real values, but I am just assuming values here. We are not concerned with the values, we are only concerned with the analysis of these data. Okay, the next point is here. Let's say this is a D point, and it has a value of, let's say, 48 inches. Say okay to this. Okay, now let's display this data in the on the catchment area. Let's say it has a single label, and that single label is of that of location. Okay, let's say its color is white, and say okay to this. Now you see A, B, C and D locations have been added. Right, the next step is to draw the Voronoi polygons, the Thiessen polygons, based on these data points, based on these point values. So you come to vectors, and then in vector you go to geometry tools. In the geometry tool you would find Voronoi polygons. Click on these Voronoi polygons, select point data 2 as an input layer, and let's say we have zero buffer region. I will let you know what the buffer means. Okay, and run this algorithm. Now you see these polygons have been created based on these 4 data points, but the Voronoi polygon or the Thiessen polygon are not exactly covering the whole area. The whole region is not completely covered by this polygon. So let's delete this layer. Increase the buffer this time again. We had gone with the buffer of 30%, I guess. So let's say this is 35%. This, let's say 40%, to avoid any redoing of this process. So this is point data 2 and buffer with a buffer of 40%. This time it is completely covered by this polygon. Okay, let's move this layer to top. Here it is. Yeah, so this region is completely covered by these Voronoi polygons. With the buffer, the area, the polygons have been located outside of this catchment area, so we don't want that too. So what we do next, we want to clip these polygons so they are fitted inside this catchment region. You type in clip here in the processing toolbox panel. Let's see this processing toolbox panel is not available. You go to this top toolbar and you right click here. There you would find processing toolbox panel. Check this panel. so it is available on the right side of your window. Clip, you see vector overlay and clip. Double click Thiessen polygons. Okay, so not these are not the Thiessen polygons. I have already created the layers before, so don't be confused. The layer which you have created, the polygon layers which you have created recently, select that layer exactly. And the overlay layer, this is the input layer and this is the overlay. The overlay layer is that of the catchment layer, because we are gonna clip this region according to the catchment region. So let's say run to this. Now you see I will turn this off too. Now a new layer has been created that is exactly fitting this region. So these are the Voronoi polygons that we needed. I will rename this clip region as our final Voronoi polygon or as our final Thiessen polygons. Okay, and you can see a chip is present on the right side of temporary layer. This chip represents that if you close this project and you wanna reopen this project again, you might or might not find this layer available for you. They might be present, they might be shown as present here, but they won't be displayed because the data associated with them would have been erased, because these are temporary layers. These are just stored in your RAM, not in your hard drive, and when you reopen your project, this layer will be gone. Okay, so you wanna save this, just click on this chip and you will be given a dialog, so you can easily save this into a permanent location. Okay, I hope you know these things. These are our Thiessen polygons. Open its attribute tab. These locations were already there in that point layer, and they have been imported from that point layer because the Thiessen polygon we have just drawn are based on those points which were present in that point layer. So the data associated with them is automatically picked by the Voronoi polygon algorithm. Okay, so comes the final stage where we want to apply our formulas as the geometric analysis is complete. Now the statistical analysis comes to play. So I hope you know the formula. The formula for the average precipitation is like this. P average is like 1 over complete area of the whole catchment, and the summation of AI into PI. This is the formula. Some may write this formula like this. For example, you have this is equal to, ignore this thing, this is P, and summation of Wi, the weightage factor, multiplied by the precipitation depth associated with that weightage factor, and that weightage factor is calculated as this AI, the small area, divided by the whole area. So this is the weightage factor. Both the formula are exactly the same. They will give you the exact same result. So you can go with any of the notations, you can go in any of the form of these formula. I am going with this form. This is relatively easier for me. You might think from this point on we need to move to Excel sheet and export this data into Excel sheet and perform the analysis. But do you know we can do all the statistical analysis within this attributable within this QGIS? How? You basically go to this what we call this open field calculator. Okay, you are seeing this open field calculator. Open this, given output field name, let's say it is AI. Yes, it is AI. So in the next step, just to give you an idea, we want to calculate the area for each of these small polygons, for each of these small Voronoi or the Thiessen polygon. So how will we do this? I say this is AI, the small area, and this area is gonna be in decimal format, decimal number. Okay, now come to this part. This is basically the Python console where you write code. So how you write code to basically calculate the area for each region? You write $sign here. Okay, let's say this is $sign, and you write area in small letters, and then you divide this area by, let's say, 1 and 6 0. this 60 means this area is going to be automatically converted into kilometer square. This project is in APSG 3857. So the APSG 3857 is a projection system where all the measurement is carried out in unit meters, and if the area so calculated would be in meter square, but we wanna convert that area into kilometer square. Okay, so let's say okay to this. Now you see the area associated with C region is this one, this one, this one. With D region and with B region it is this one. This okay, so the first part is done of the formula. We have calculated the AI. Now in the formula you would see it was PI into AI. So we want to multiply this area with this depth. Again we are going to go to the open field calculator. At this time we say AI into PI. Remember, this is just a name. This star doesn't mean it is in real time multiplied here, but we are basically going to multiply these two quantities right in this console. Okay, come to this right side, you would find here fields and values, and pick this PPT depth, double click on this, then put a star in the formula by just pressing shift and 8, and then come to the AI and double click. Okay, so in this way the precipitation depth will automatically be multiplied by the small area, the AI. You see, another column has been added where this AI is being multiplied by this precipitation depth. So far so good. Let's save this attribute table to have an updated attribute table. It is saved now. The same thing you are going to do with the catchment basin. So go to the catchment basin, open it attribute table, and again you are going to open the open field calculator. You are going to enter $era divided by 1 followed by 60 to give the area in square kilometer, and I have already calculated this area in square kilometer, which is coming out to be 12171.807 kilometer square. So no need for me to calculate it again. I have shown you how to calculate it. You can do it yourself. So the next thing is to sum of AI and PI, and then divide this sum by the area of this catchment basin. And that's all from my side for this video. I hope you have enjoyed this tutorial, and I hope this was helpful, and I hope it will help you in your analysis and in your estimation of aerial precipitation data. If it is really so, kindly like this video, and don't mind to subscribe to this channel to sort of help me make good videos for you in future. Thank you so much. Goodbye.